All right, everyone, we're going to go ahead and get started here. My name is David. We're going to be covering a SOLIDWORKS simulation webinar. If we haven't met before, I'm out of the Houston office, and MLC is one of the 5 largest VARs. I'm sure you got an event invite straight from us. We've been doing the SOLIDWORKS sales demonstration and technical training product support for over 38 years. We've been doing since the first release of SOLIDWORKS, and we're your value-added reseller for not only SOLIDWORKS, but Mastercam and Marked Forge 3D printing solutions as well. As I said, my name is David. I'm out of the Houston office. My background is primarily in oil and gas, though I do have some machined and thermo injection experience as well. I graduated from University of Houston, and I'm very much into hunting. MLC is headquartered out of Austin. We do have areas where in the Northwest Pacific area, for example, where we only do Mastercam, but primarily all over the South we do SOLIDWORKS support. For today's webinar, I'm going to give a simulation overview, some of the product capabilities. I'm going to go through a case study here of a thermal example using simplification. Then we'll jump into a static analysis using symmetry and discuss some further simulation capabilities. Now, some of the things that we look to gain, or I'm trying to add some value to your workflows with out of this webinar as well, is kind of discuss different element types, meshing strategies, overall strategies for improving your simulation performance, decreasing your simulation solve time. And then I'll go over some of the training options if you want to explore any of these topics and get more in-depth overview. At the end, we'll open it up for questions and discussion time and whatever feedback you have. So with that, we'll go ahead and get started. So simulation, just like SOLIDWORKS, comes in 3 different flavors. So we have simulation standard, which gives you static, fatigue, motion, and trend tracker capabilities. Then we move on to simulation professional, which gains you some of the heavy hitters here would be optimization, thermal, which we'll look at today, but you also get frequency, simplification, which we're going to be using, and a lot of connectors, buckling, and some other items as well. Premium is going to be where we have all our more advanced studies like dynamic fatigue, dynamics, nonlinear, and composites. With that being said, let's go ahead and jump into the case study that I've got, and we'll discuss some of these tips and tricks, if you will. So first thing that I want to explain is just a little bit of the problem set that we're going to go to. This is an expansion bellows, or an expansion joint that's going to be under a pressure thermal load. Our goal of this study, for the case study here, is going to be to analyze the thermal loads that we've got on this joint. And then we're going to do a second study where we include the results of that thermal analysis as an input to see the static stresses that we get from it. Now, before we jump into either of those studies, I wanted to point out a couple things that's been done just on the CAD modeling side here. You'll notice that I've got a cut here at the bottom of my tree, and if I roll that up, you'll see I've got another half. So this is what the full joint looks like. Part of this is, of course, improving my study time. So what I've done before creating my study is a little bit of FEA or modeling prep. This is a common practice. One way that you can accomplish this and get your FEA models or modifications ready for simulations by taking advantage of configuration. So here I've got a symmetry configuration that has the cut unsuppressed, which is turned on in SOLIDWORKS terminology, and then I've also got a default one where basically it's just hogging whether this is suppressed or unsuppressed. So that's what I've done on the modeling side. I've just cut my model right in half, and I'm ready to go ahead and start my study. As I was saying, I want to start with the thermal study because that's going to be an input for the static analysis. That's the one that we need to do first. So with my simulation add-in turned on, and if you don't have it turned on, you'll go to the drop-down arrow just to the right of your gear symbol, take a look at your add-ins, and hit the checkbox for SOLIDWORKS simulation. The left side, by the way, will turn it on just for this current session of SOLIDWORKS. The right side, if we hit it here, the add-in will be turned on by default anytime we launch the software. So if you use it a lot, go ahead and check the right-hand side. But once I've got the add-in turned on, I can take a look on my Command Manager tab up here in the right for my simulation and select a new study. Here's where I'll define the study type that I want. And again, coming back to the capabilities and just the breakdown of the simulation products, this thermal analysis and simplification is something that is covered in our simulation professional package. So I'm going to go ahead and leave this on thermal simulation, and I'm going to also take advantage of 2D simplification. So there's two ways that I'm already adding efficiency into my simulation analysis, right? First way was by adding that cut, and I'm going to use symmetry, which I'll get to in my analysis setup. I'm also going to hit the checkbox when I'm creating the study to use 2D simplification. Now, some of the reasons why we would want to do this is, of course, to decrease the solve time. So by doing this, the amount of geometry that we're going to be applying our mesh to is much smaller. So that allows us to have a much finer mesh, much more calculations point without having to wait a much longer time for that type of mesh to fully go through if it was a full 3D model. So I'm going to go ahead and choose the checkbox for 2D simplification now. There's a couple of ways that we can simplify this into 2D. One would be extruded, and there's a couple prerequisites that we discussed in our training class for that, whether you have plane strain or plane stress. For this one, we've got an axisymmetric model, so I'll go ahead and check the checkbox for axisymmetric, and then pick a plane that I want to analyze it. So I'm going to be looking at a section, just like I took a section view about this front plane here, and then I want to specify the center of the geometry. Now, this is by a reference geometry feature. I just added my axis just like you would add a plane, and I'm going to use that for my 2D simplification definition. Go ahead and green check, and we see I've only got half the model over here, and we've cut the model so that we've got it in 2D. Now, the SOLIDWORKS material was already applied in my CAD model here. If those of you are new to Sim, the tabs to switch back from your model to simulation are down here in the lower left corner, kind of like where they would be in Excel. If I switch back to this model tab, each one of these components has already got a material specified, and that's why it automatically came in defined over here in my SOLIDWORKS simulation tree. Now, I always recommend that regardless of what type of study you're running, just to make sure that you're defining everything, not missing things, and that we're setting it up from the get-go how we want with the types of elements that we want, the connections, all that kind of stuff. I work my simulation tree from top to bottom, regardless of what type of study is. So from top to bottom here, I have my study name, which was Thermal 1, and then it's parentheses giving me which configuration of the file I've got. This is, of course, an assembly file, and I showed earlier that we had a symmetry configuration that had a cut that was unsuppressed. Below that, I've got a list of my parts, so I've got a part folder. If you want to add a material here, the point is that you're not applying that material back to the CAD model. So you're not changing any materials for your production prints. This allows you to take advantage of, not only analyzing the parts or the files with what you've specified, but what if it doesn't meet your criteria, or you want to check out some different options for cost reasons? You can change the material here in your simulation tree without affecting your model or your drawing. So I just wanted to point that out. This triangle here in the left of each of the file names, that's letting me know that's the symbol for a solid mesh. Now, I'm going to get to some tips and tricks a little bit later, but there's 3 different types of elements. We have solids, beams, and shells. So that triangle is telling me I have solid elements. And if you're using 2020, you'll see those teal colored tetrahedrons or pyramids, if you will. That wavy or curvy tetrahedron indicates I also have high quality elements, right? That's the default that I've set up in my simulation options. So I typically always mesh my parts using high quality unless I've got some specific circumstance or I'm having some kind of problem that I'm trying to troubleshoot with the mesh. Now, the first thing that I'm going to do is go ahead and start walking down my tree. I've got an assembly, which is where my connections will come into play. For this analysis, the bonded is the valid component contact that I want to use. So I can come over to the next one and start applying my different loads. For this one, I'm going to right click, and in general, anything that you want to apply in your simulation tree is typically via a right click. So I'm going to right click on my thermal loads and specify a temperature. Now, I'm not doing a time-based or transient study, so this is a steady state temperature. I'm not looking at it any kind of temperature to develop over time, or I don't need an initial temperature. So here I'm going to go ahead and just change my units to Celsius and specify 220 degrees. Now I want to place the edges because I'm in 2D, so I'm not clicking faces. I'm going to go ahead and select the edges where that goes. So that's going to be on the inside of this joint. So I'll click that face, the end of the wavy piece, and I need to get the whole inside of this one. And a real quick selection method is just to put my cursor over the edge, and I'm going to right click here and say select tangency, and that'll grab all of those different ID edges that I want. Go ahead and select the green check, and my 220 degree temperature load is applied. Next, I want to specify the mechanisms of heat transfer. Now, you'll notice when I right click on thermal loads, I've got convection, heat flux, heat power. I don't see conduction here. That's because conduction is the default mechanism of heat transfer for SOLIDWORKS thermal simulation. So if I've got two faces or two solids that are touching, I don't have to define that as a conduction. It's going to look at the material properties, take that into account, and I don't have to do anything as far as my study setup is concerned. But I do need to specify the places where I have convection. So I'm going to right click, say convection, and for this I'm just going to do the same. Let me clear my selections in here. I want to select this first fillet and then walk around all on the outside. This joint meets up to another piece over here, so that's why I don't have the convection past that fillet. Get this one, and for this whole outside I'm going to do the same thing I did on my temperature load on the ID. I'm going to put my cursor over the edge. I'm going to right click and say select tangency to get all that. Now for this I need to go ahead and put in my convection coefficient. For this material I've got 50 watts meter squared Kelvin, and then my ambient temperature in Kelvin is going to be 298 degrees. I'll go ahead and green check that out, and I'm ready to break up my model into calculation points or mesh it. So I'm going to right click just like I do on any of my other inputs for simulation, and I'm going to go to create mesh. Now I always suggest as a first run to use curvature base. I discuss the different types of meshing in our class a little bit further. Standard mesh is basically when you need a symmetric mesh that's not going to adjust around curves in the model or geometry. Blended, of course, is mixing the two, but for a first run, I always suggest just putting it as curvature. We give some other tips and tricks for meshing in the course as well. I'm going to cut down my maximum element size, which is this top box here under my mesh parameters. I'm going to use 0.97, and I can crank this down even smaller if I like, because again, I've cut down on my solve time already by using the symmetry cut. I'm going to specify that, and then also using 2D simplification. So let me go ahead and specify 0.97. We'll green check that out and take a look at what it looks like. Now I've got my recommended minimum minimum number of elements. I want at least 2 through the thickness here, which you can see represented by our mesh triangles here. So it looks like I've got my just rule of thumbs mesh parameters already considered. Let's go ahead and run this study. Solves extremely quick. Of course, I've only got what you see here is this section surface that I'm analyzing. And before I move on, I want to show that this, just because we're analyzing this in 3D or 2D, sorry, doesn't mean that I can't get the results as if they're in 3D. So if I right click on my thermal plot, which is the only result plot I've got by default here, you can say show as 3D plot, and then it'll give you that as if you had analyzed it in 3D. So you're not losing any data by taking advantage of the improved solve time using the 2D simplification or symmetry restraints here. All right, so with our thermal study results already completed, we've got our input and we're ready to start our static stress to see the results of that thermal load. So here I'm going to go ahead and just start a new study. This one will be static, and I'm going to of course use 2D simplification again, cut down on my solve time, and just like before I'm going to specify the symmetry. So I'm going to say axisymmetric, same plane, which is the front, and choose my axis. Green check, and we're ready to go. Now before I get started, I want to include the results of that thermal study. Now to do that, I'm going to right click on the top of my simulation tree where my study name is and access this study's properties. You'll notice that there's a tab. The second tab over is for flow or thermal effects. If you guys are running flow simulation or CFD analysis with SOLIDWORKS, you can also include results from that as well. Maybe you've got wind and want to look at stress from that, or temperature loads from flow simulation. The process is the same. So here I'm going to go ahead and rather than using an input temperature, I'm going to say I want to input a temperature from a study. If I have more than one thermal study, I'll get an option to select which one I want to use. I'll specify that here. I'll use the same reference temperature at 0 strain and go ahead and click OK. So now you'll see that that shows up under my thermal load here, and that again is just using the results or the load from my thermal study that we just ran. I've got the same materials that I'm not going to vary from for this study, of course. Bonded, of course, is what we want, and I'm ready to move on to my fixtures. Now, first thing that I'm going to do is in my static simulation is let it know that there's the other half of the model out here that could affect the rigidity stiffness, of course. So I'm going to right click on my loads, and instead of going to fixed entity, I'm going to jump straight via right click into my advanced fixtures. Now this is just a tab. You'll see the standard fixtures are right above. You can access it if you accidentally clicked fixed by clicking the down arrow next to advanced. I'm going to use the first one, which is symmetry, and then click on the face that was cut. So there's only one face that I need to cut here. I'm going to click right there, and you'll see I only had to click the face on this bellows, not the flange, but it knows that everything to this side is the same, and this is the only face this would cut, so I only have to click that one edge. If I had cut more than one component, I would need to click every edge because I'm in 2D of the faces that were cut. I'll go ahead and green check, and I'm ready to add my next fixture. So this expansion joint will of course expand along the length or axially this direction here. So I'm going to do that as a displacement. I'm going to right click and go straight back into my advanced fixtures. This time I'm going to use reference geometry. I've already got the front plane selected here, and now I'm going to say that this edge has a displacement and our translation in this case of 4 millimeters. Now it depends on which box you're putting. Notice that this bottom box for normal to the front plane is grayed out. That of course was because it would give me a load or a fixture that is out of plane with my symmetry. So you can't go out of plane here. The other two options other than normal are along the plane in direction 1 or along the plane direction 2. For this one, I need this first one, and I'm going to go ahead and put in my 4mm displacement that I know this thing is going to expand. We'll go ahead and green check. Now, in addition to the temperature, this thing also is subject to a pressure load. So we'll go ahead and specify that by right-clicking on our external loads and selecting pressure. For this, I'm going to use a similar process like we did in the thermal study. I'm going to select these first edges where I've got the pressure load here. And then just like I did on the previous study, I'm going to right-click after hovering over the edge and use Select Tangency to grab the entire ID there. It's going to be 0.3, and I need to change my unit here to megapascal. So let me just make sure I've got the right value in here. 0.3. There we go. Green check. And we've got our pressure load. Now, this time, I'm doing a static study, which requires me to have a little bit finer mesh, a little bit more detail. I'm already in symmetry, so adding some mesh controls or localized mesh, where it's not meshing the whole thing, just a localized area, the mesh controls, is not going to be much of a problem here. So to add a mesh control, I'm going to right-click on my mesh. You always want to add the controls before the global mesh so they can attach to the localized mesh controls or area of focus, and select Apply Mesh Control. Now, for this, I'm going to just use this whole cross-sectional body. So I'm going to click the face, again, the 2D face here, and then for my maximum element size, I'll just use 0.45, so about half what my global was. Go ahead and green check, and I'm ready to go ahead and add another mesh control. I'm going to right-click again, say Mesh Control, and add these 3 edges here that are kind of small. I'm going to add a few more elements to this small area where I've got some geometry change. This will be 0.45 as well. Green check. And then I'm going to right click and we can apply our global mesh. So I'll say create mesh. I'm going to use my curvature base, of course, and the same max element size. Doesn't have to be, but we'll use 0.97 again. So go ahead and green check. We'll look at the mesh. We see we've got the finer elements around our areas of that we've applied our mesh controls. So instead of 2, now I've got about 4 or 5 elements through the thickness. It's going to give us a lot more data points for our calculation solver. So let's go ahead and run the analysis. So I'm going to right click and say run. Solves pretty quickly. We're seeing those that movement there from the displacement that we've got. Again, we can look at these stress results here in 3D if we like. This time I'm going to do it another method. I'm going to right click on my stress plot here and say, instead of show as 3D plot, I'm going to say edit definition. Another way that we can get into that is just by this definition here and say show as 3D plot. And I went ahead and went into the full menu here because I typically come into the chart options and I like adding a max annotation. I just like it to tell me where my max stress is without me having to look and zoom in and out throughout my colors all the time. So, of course, it's going to show me the max stress where we analyze the section. It looks like this area here, right in this groove, is the location for our max stress. Now, if we want to see what that is compared to these others, one thing that we could do is right-click here and just probe. Select different areas, compare that. You can plot these on a graph if you want to see how stress changes as you move out of the radius, for example. But this is where our max stress is, right? Now, before I can say that this is truly where my max stress is, a couple of things that I would want to do here would be to validate my mesh, validate my studies. Now, this is something that I'm going to save for training classes. I don't quite have enough time to go through everything. There are 3 or 4 different ways that you can validate whether your mesh is a good mesh. And ultimately what that means is, are your results valid, right? There's a couple different rules of thumb we can use. One of them being, aspect ratio, looking at energy norm, looking at elemental versus nodal stress, and of course just meshing finer and looking to see if your results change within a couple %. But I'm going to go ahead and take it into account that this result is going to be good. So kind of coming back through what we've done here is first on the model side, we added a cut just to simplify and our study setup and reduce our solve time. Then we came in and did our thermal analysis first that we set up as a 2D analysis, specified our mechanism of heat transfer, our temperature input, and then ran the analysis and then brought that result to look at the stresses that we get from that thermal load. So that's the overall process whenever you're running a thermal study or looking at the stress results of a thermal study. We'd first just do the thermal and then bring that into the static.